It's not that complicated because it's just the introduction of what is it actually is. Just a very brief introduction. Then like if you always see any mistakes in the slides, you can just point out, because honestly I'm not too sure about it because I haven't attended any machine learning classes. So for collaborative, this will be the structure. So we'll be talking about collaborative filter. Then you'll be creating creating our own custom layer. Then after that, it will be the inside of the training loop. Then for collaborative filter, it's just we make a prediction based on how others feel about this particular stuff. For example, in their example is the movie lens. Like for example, if someone have a similar taste to mine, then if they like this movie, then most probably I would like it also. So the very basic way to make this is to use a dot product. They use the embedding matrix, two embedding matrix, and they just dot product the result. Then after that, they try to minimize the mean square error. Yeah. Then they just change it while changing the mean square error and minimizing it using gradient descent. So this is just like shallow learning, yeah. Because you say something like deep learning, but it's not really deep. That's why it's shallow learning. Then they use this her/Chi/Ming initialization to randomize the initial value. It's some normal distribution. So they use this normal distribution with a standard deviation of square root of 2 over the number of things in the previous layer to get some randomized value for the initialization. So for this, it's just metric product, dot product. So it's quite simple to understand. So dot product while changing the embedding matrices. Then next will be on like how to make it even better. So what he went through was that he added an additional bias to it. Yeah, this bias like make it so that like, because some user may like all movies better than the others, so there's a normal like shift in their ratings. So you put the bias in to like filter it out. Yeah. So it's also, you also do the gradient descent on the bias also. Then use a sigmoid to make it so that there's a minimum and a maximum ratings. If not, if you don't use a sigmoid and have a minimum maximum, it may overshot your maximum value. Yeah. So and he mentioned something about broadcasting your bias, since it's only a vector and you need to do a matrix multiplication on it. So anybody have any idea like what is it? Like broadcasting.
So broadcasting is a feature in NumPy in which when you, like, let's say you want to multiply a 4x3 matrix by a 4x1 matrix, yeah, and then so you're not able to do that because the dimensions don't match. So what NumPy will do is it will take the 4x1 matrix and then expand it such that it's able to be multiplied by the 4x3 matrix.
Yeah. And that's basically so you use the squeeze. You use the squeeze in this PyTorch or NumPy, I think, to make it, to broadcast it. Now this is basically the code.
So do you guys want to elaborate on what squeeze and what it actually does?
The actual.
You say because the dimensions of the matrix are not of the same size to allow to multiply, then what does the squeeze operation do to do that? Right. I mean, he does gloss over quite a bit of detail, and that's fine if we're just concerned about practical implementation. But the reason why we are doing this as an NUS course is, exactly what he poo-poos in his lecture. We don't really care about the math. Actually, we do care about the math quite a bit. But we would like to actually know what's going on with the code that's going down, right? So this is one of the first more detailed lectures where he's going through the code in more detail. But it's not at the level of depth which we would like.
Yeah. And anybody know like how it's actually implemented?
It
Like how
says removes single dimensional entries from the shape of the so
Remove single dimensional. Do you want to paste that into Slack or anything? A link to the documentation for that, so that those of you on Slack can go pick up what they said. I mean, if you guys are all clear about it, and I'm the only one in this room who's not clear about it, that's fine. But I have a hint that maybe some of you are not clear about it, and it's just like, okay, well, it's being glossed over, so I guess I don't really need to know about it. But we would like to know about it, right? Because eventually, if we're going to be deep learning experts, we're going to have to write our own code. And you know, we've already watched the videos, so that's fine. Now we want to understand what's going on. On the wrong Slack channel. Thanks, Rrubaa. I realized I put it on. Thanks for doing that.
user bias.
Yeah.
This one here.
Yeah. No.
So what is this code actually doing? You're taking an embedding vector, right? Just a vector. And you have a bias term, which is a single scalar, right? And what is it trying to do? It's trying to do a dot product with the bias. Is that right? I don't know. So I'm just guessing.
It's doing the dot product of the user vector and the root vector, then adding the user bias and bias after.
Okay. So you have a single term for the bias, is it? Or a vector?
Yeah, so the bias is universal, the same for every user.
And every user and every item. Is it the same bias term for both users and item or separate bias?
Separate.
There's a separate one, right? There's a
Yeah.
UV and I guess there's an ID or something, right? Okay. But are we clear about why there's only a single bias term? I mean, if you don't know, then say so. The puzzled look on your face is either tells me this is either too basic or it's like I have no clue what he's talking about. No clue. Okay, so does anyone want to explain a little bit about how the neural net is set up, why we need a bias term in the first place? I think it helps to just, I mean, it's only 10 o'clock in the morning, right? We haven't had our coffee. So what is the bias term? I'm literally having my coffee. But do we know why we need a bias term?
Because some user tends to give very high ratings, so we want to correct those. Problem, right? So add a bias term.
Neural networks, you kind of want to in neural networks you want to classify and you want to set a sort of threshold over which you want the value to be 1 or 0. These
Okay.
are the bias.
Yeah. So I think both of you are right, but in Zhang Kan's point is a very high level one, and Radhika's point is a little bit lower level. So if we don't have a bias term in the neural network, what happens is you can only classify things that go through the origin, right? So if you're trying to build a linear classifier, which is what a neural network is trying to do anyways, right? Sorry, let's say you only have one neuron, right? So, you know, a perceptron or something very basic is only going to allow you to draw things like Wx plus b. This is your bias term, right? So this is a creation of a line, right? So if you're missing this, what can you do? Basically, you have y equals wx, right? Or as we know from, I don't know, primary school, this is mx, right? So this is the slope. It can only go through the origin, right? But many times we have data sets where it's not like that, right? We have something like plus, and then minus, 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 and then if we do anything through the origin, that would be right. So you need the bias term to have the intercept be something other than 0. Right? If we wanted to draw this line, obviously that would be y plus some b, whatever this b is, right? Okay. So that's why we need a bias term. So no matter how complex the neural network is, let's say you have this W be a matrix, right, and X be a large matrix. If you don't have the intercept term, it's still going to be some polynomial function that passes through the origin, right? So you still won't be able to get bias equivalent. Okay, so that's what the bias is for, right? So even if we have a lot of different dimensions, like in an embedding, right, you can define how many dimensions you want your embedding to be, right? You're going to basically end up with a fairly complex polynomial because the x will be in the size, at least one of the dimensions will be in the size of the embeddings, right? The other one will be in the size of the number of data items that you have, right? So you still need the bias term in order to get things to come off of the origin, right? I mean, the bias term is not so important if you're doing one other piece of work. That's normalization, right? So we've discussed that a bit. He says it's generally a good idea to normalize your data, right? So take the range of a feature, whether it's an embedding vector or any other piece of data like structured data, and then normalize it so it has a unit variance or something of that sort, right?
Do we remove some extraordinary values out of it, like outliers, before normalizing? Because if you normalize with outliers, technically the result will not be that.
Yeah, so that's a really big problem. You probably want to do some pre-processing of your data to normalize it, to throw away outliers or treat them in some way, right? Otherwise, if you just normalize with outliers, you could be compressing the useful part of your data to a very limited amount, right? Imagine like most of the values that you have in your data set are between 1 and 10, but for some reason, because of some noise, you have one particular point that has a data of 1 million, right? Then if you normalize, everything will be squished into a tiny spectrum for that particular dimension, and it might not play well with the other dimensions.
Do you do some transformation also, like log transform? Because
yeah, you can do some sigmoid, right? Sigmoid will help you a little bit there, or you can do a log transformation, which some people do, especially in natural language, right? Are you guys all familiar with why we do log transformation in natural language and other events? Okay, so let me just spout off 3 minutes of story. Okay, so when you do consider natural language, let's say you're doing document classification, all right? One thing that you will say is the documents class might be dependent on the vocabulary in the document, right? So if I say oil and Venezuela and crude, then you probably have some idea it's about oil forecasting, right? But if I say the word IBM, you might think it's technology stuff, right? But the word computer could be in many different documents, but for it to be about computer, that word has to be mentioned several times, right? But we wouldn't say 100 mentions of computer is very distinguishable from 101 mentions of computer, right? Whereas if you had 1 mention of computer and 0 mentions of computer, it's very clear that there's a distinction. And 1 mention versus 2 mentions, well, 2 is definitely more topical. But 100 and 101, there's almost no distinction, right? So when we take a log value function, it has that nice decay. It's exactly the same type of thing as what you would do with a sigmoid, right? So you're just saying, yeah, it's frequent enough that it's an indicator, but you don't want to make it too much, right? So that's the same idea. So that happens in a lot of signal processing work. So you can think about sound. If you do sound and music processing, you know about decibels, right? The decibel scale is also a log scale. So we can't really hear the difference between very, very loud and very, very, very loud because they're all just too loud for our ears. Okay, so that's another quality that we do. But we can distinguish very soft and very like low frequency pretty well with our ears. So this is a natural phenomenon that happens in language, it happens in vision, it happens in music and sound. And so you see a lot of treatment. When you see a log, you should be thinking, oh, that just means some type of feature like that. So when you see equations and you see a log, you should know what it means. It's not. It's usually not a fact. It's sort of like an empirical convenience. Yeah. Okay. Okay. So enough. That was my 3-minute lecture for today. Carry on.
Yeah. Then for this line is the setting of the minimum and maximum. Since sigmoid, you can only go from 0 to 1. 0 to 1. That's why you with a sigmoid multiplied by the range of your rating, then plus the minimum rating, then you always be within the range. Yeah. So next. So after that, he went through the neural net version, which is use all the embedding matrices of the user and embedding matrices of the movie. Then he concatenate it together and pass it to a 10 by n plus m matrix, for example. Then after that, he pass it to Relu. Then after that, he pass it to another matrix that multiplies it to 10 by 1. And this is a linear, yeah, quite a linear neural network in a sense, I think. Yeah, so for this line, this is like the declaration of the matrix. Of the matrix over here. Then this line is this matrix. Then after that, for this line, this is just he included dropout for this case, which I think we already covered in the previous talks, like what is dropout. So he drop out, then he pass it this concatenated matrix. Then after that, yeah, then the dimension, yeah, then at the end comes it returns the value. Yeah, this is the same. This is the same as the previous one. Yeah. So, yeah, anybody have any questions about this code?
Do you
How it
guys
works?
understand it? Because I don't. So. Why is he catting the two matrices together? I mean, this is a common operation you see in deep learning, right? You just stick two vectors on top of each other and you just hope for the best. Why do they do that?
I thought the intuition is that the U is kind of user image movie. So those are supposed to be embedded. Now they just put them together, see it as one whole big categorical variable, and then try to fit them.
So what does one of these vectors mean semantically? Does it have a meaning? When you cat one vector of U and one vector of M. You guys have any insight on that?
So I don't think.
Go ahead.
Yeah, go ahead.
I don't think like catting makes a huge difference from just heading. So like from what I understand, like from my previous work, the idea is to bring both users and movies into the same space. So like
So we could do it by adding, we could do it by multiplying. Why catting?
catting gives one.
Okay, so the empirical validation. It does better, so we do, huh? That's okay.
Yeah, but it's computationally more expensive.
Yeah, why is it computationally more expensive?
Because if you cat, then your vector length is longer.
Okay, everyone got that, right? So you have a longer vector, there's more computation. But Jeffro said you could as easily add them together because they're the same length, right? Is it? They're the same length, they're all size 10. Yeah. So would that put them in the same space? It would, right? But why wouldn't we want to do that? Why does that give lower accuracy?
You lose a lot of information, right? same value can be obtained by adding two different sets of numbers.
Okay, so I think both of you are saying similar things, right? Shen Hao is saying, you know, I could get the same sum by adding two different sets of numbers. So there's several ways I could arrive at the same value, right? And then, I'm sorry, your name is?
Martin.
Mathieu was saying that you're losing information, right? So losing information is sometimes a good thing, and sometimes it's a bad thing, right? So when is it a good thing to lose information?
When it
When it
improves
doesn't
your
contribute
results.
much.
When you're overfitting, right? Does everyone get that? Overfitting means you're learning the training data nuances, right? So it might be that adding the vectors is just fine when you have a small data set, right? Because you don't have enough information to estimate your parameters well anyways. So why don't we just put everything into the same embedding space? So let me give you a thought experiment. Would it be better to add two 10 length 10 vectors together, okay, to get a length 10 vector? Or is it better to concatenate two 5-dimension vectors? You get what I'm asking? I could either add two 10s and get another 10 out of it, or I could concatenate two 5s together to get a 10. I'm going to end up with the same number of operations. So which one is better?
Second one is better because you have 2 and 5.
Okay, so the second one might be better because we are separating the influence between movies and users, right? It could be better. It might not be better. I guess, again, we can say, well, will the accuracy go up, right? Cross-validation, does it improve or not? But our hope is to establish some notion in our head, some thought experiments, right? To say, what do you think is going to be the result? And I see this problem all the time with people that do deep learning. It's like, heck, I don't know. I'm just going to run the experiment first and find out, okay? But that's not how you want to do data analysis. If you're in a PhD program, your primary mission is to come up with a hypothesis, execute experiments to validate, not find out what the answer is, to validate your output, okay? It's a very different mode of operation. That means in your head, you should already know what the outcome should be, okay? But you just execute the experiment to ascertain the significance of the results. And you should be surprised if it doesn't go the way you planned, okay? But because software is so easy now, you know, I just go to sleep, next morning the results come out, I look at the plots, do whatever Seaborn or visualization. Heck, that one did better. I have no idea why. I'm not going to think about it. You know, I'm just going to be like the machine, just optimize, 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 right? That is not what we want to do. Okay, so I encourage you as we go through, think about why is it done like that? Why does he say, oh, it gets better results? He doesn't even tell you why, right? Sometimes it's like, yeah, well, this is the best hot thing off the press. You know, no one else in academia is doing that. So what? Yeah, it may be, but you know, as academics, we want to know why, right? Because if you don't have insight, you can't improve things, right? So that's very important. Okay, so please think about those, right? So is there a case when adding the two would not be a good thing, right? So just now, I'm sorry, this gentleman in the back, what's your name? Raja said, maybe it's better to preserve the semantics by keeping those 5 and those 5 separate because they're semantically from different items. When would that not be a good idea? When would it be better to use, let's say, a different number of dimensions, maybe 7 from movie and 3 from users? Okay, so Sylvain says maybe the representativeness of the data might be a good thing, right? So if I have a few number of users, maybe I don't need so many dimensions, right? Or if I have a lot of movies, maybe I need more dimensions of those. Or maybe all the movies, I have a lot of them, but they're all sci-fi or something. So actually, I don't need so many dimensions for that, right? Because they're all cross-correlated. You know, their entropy is not very high. Anything else you guys want to think about here? How would we set the number? Oh, sorry, Jeffro, go ahead.
Wondering why there's a minus 0.5.
Minus
What- how does it
0.5.
contribute?
What's he doing there? Okay.
He's actually making
Continuity.
we're actually making it symmetric to 0. When you have sigmoid, you have sigmoid from 0 to 1. When you
Alright, yeah.
subtract
Yeah.
0.5, it is actually making it symmetrical to 0.
Yeah.
That's why we use scanner function.
E minus first. Then scale.
After your transform.
Yeah, sure. It's like minus first and scale.
Yeah, it should probably
Yeah,
be
but the signal
the
gets scaled,
sigmoid term.
So sigma is 0 to 1, then he scales it
Why-
between min max, then he adds the min rating and subtracts an arbitrary number. That's how it looks like to me.
Yeah. I mean, if he was making it symmetric, it would not be a big.
So maybe there's a bug in the code there, right? It could be. I mean, people are flying by the seat of their pants. They don't check their code correctness. Then maybe there's a problem. Because if it still works, who cares? There's no bug, right? There is a bug, right? The problem is because it still works, you don't even check. I have that problem all the time. Sorry, go ahead.
Now we have a hypothesis. It should work better if we put -5 in the front.
Okay, so you guys can go try it out, right? Because we say here maybe there's a problem. And then when you finish your check, if it does work better, you can issue a PR. Why not? Okay. It doesn't take long to test. I mean, you guys have the cats and dog data set, I guess, if you've been following like you're supposed to. I actually haven't been following the course. I still haven't set up my environment yet. But hopefully you guys have been better and more diligent than I have. Other parts? Anything else we want to say about constants or order of operations? Like why 0.75 for dropout? Because it works. Crappy answer.
Or maybe it's just this is empirically best.
That's another way of saying it.
Yeah, exactly. That's a more politically correct way of saying it. You can read all this bullshit in scientific archive papers, right? When they see the word empirically validated, it means we have no idea, right? We just ran the darn thing because we had electricity to spare.
Because it depends on whether your model is overfitting or not. Then you decide whether you want to increase the dropout rate or decrease. So literally, I don't think there's a valid justification on why they're choosing 0.75.
Okay, do you guys agree with that? I mean, there's a lot of things in contention. The number of data items you have, the quality of the data items, your neural net architecture, which level that you're employing dropout on, whether it's the input level or hidden layers, or which level of the hidden layers, right? There's all those optimizations you can do. And probably somebody will write a paper saying how to optimally set dropout for a certain architecture, right? If it's not already written.
Yeah, the loss.
Improves. Okay, so
But you could just use like energy still.
yeah, still you can issue a PR against that code. Why not? Okay. I mean, the library is new. It's not that old. It's not, 6 months old. It wouldn't be surprising if there are bugs in it, even for the #1 Kaggle competence editor. Again, another thing that you guys should be doing as PhD students or student researchers in general is, don't trust outputs just because they've done better. Yeah. You actually have to know from ground zero that your things are working the way they are. There's nothing more embarrassing than publishing a paper as a PhD student and then having to retract it because you had errors in your analysis. Okay, so don't trust everything you see just because it works well. We have plenty of cases, myself included, which we had to go back and say, oops, we made a mistake. Hopefully you catch it before you publish your work. That's all I have to say. Right? So how do you do that? I think if you listen to the Stanford lectures, the vision lectures, they went over that a bit. And I think they're, of course, because them being Stanford, they're more academically inclined. They say, make sure you try it with toy data sets, small data sets that you absolutely certainly know what's going on, like a data set of size 5, right, with only 3 dimensions, with 2 users. I mean, you should be able to make the math work on your own, right? Stochastic gradient descent or not, you should be able to solve those gradients on your own and be able to figure out what the value should come out to be. If you do that and you are able to match, which they advise, you actually want to check that your gradient descent is working properly. And so you solve it analytically on your own after trying out the software. And, certainly trying out the software is the best way to start with, right? But because if it doesn't converge, you have a problem. But even if it does converge, you may not know it is converging to the right answer, right? So you then have to go back and check your results afterwards. Go ahead, sorry.
Oh, yeah. Yeah, then after this is the end of the custom layer thing. So now is the how the training loop actually works. So actually, for the training loop, the initial one they gave, the initial explanation they talked about was using the finite differencing of approximation. So basically, it's just approximation of differentiation. Then you just adjust it accordingly, just bit by bit using this approximation. Then he mentioned something about Jacobian and Hessian. Yeah, so anybody have any idea what it is?
Please explain, yeah. Go ahead.
Matrix
Yeah.
of the partial derivatives.
You want to go ahead and give more detail?
It's in a second.
So like if you have a function xy, then the matrix would be a 2 by 2 matrix. D2 over d x squared of fxy, and then d over d dx fxy, d over dy, d over dx fxy. And then
You want to write it down?
Board, please.
the Hessian of this would be
Yeah,
Maybe
it should be a five.
It's just you just pull it up and put it in the slides. Yeah. However, that's it.
Should be 2 squared.
Yeah,
If you
second degree.
second derivative. You're saying a second derivative. In the numerator 2 squared. In the diagonal.
The first term and the last term will be
Yeah.
square.
他们放 square.
Oh, okay, okay.
哦，这个是前后。哦。
So can anyone explain that without the math? What does it mean? Second derivative of what? Why do we take the Jacobian and the Hessian? Why is it important for us?
So when 0, then you know that the gradient is steeper.
Gradient is steepest.
Yeah, so like, you take first derivative, then you solve second derivative plus 0.
Actually, I know it from math perspective only. When you take single derivative, you know when it's one term. When you take a double derivative, you know whether it's maximum or minimum. This is what in the maths.
Okay, so it's just generalization, right, of the concepts in just general calculus, right? But we're just doing it for linear algebra, which is a vector form, right? So just like Jeffro said, we take and Rajan, right? Rajan said we take the second derivative, which is as the code name of Hessian, right? If you want to confuse anyone, say Hessian, right? And so, yeah, just to know when things are at a maximum.
Jacobian's first derivative.
Yeah, the Jacobian stuff.
Just to understand what you said, equal to 0 is something about the inflection point. Something, the graph is.
So Hessian is the Jacobian of the gradient.
The Jacobian of the Jacobian.
Yeah.
Gradient.
Yeah.
It's the Jacobian of the gradient.
But what you said on the Hessian is 0, that has the meaning of an inflection point where I think it's like
Inflection
this,
point of the gradient. Of the gradient.
Do you want to do it like on a single variable? I mean, we everyone here has taken secondary calculus, right? Secondary school calculus, right? So shall we just? Do we need to make that clear? Maybe you want to draw it out.
So let's take a parabola. This parabola, it could be upward or downward curve. This is y is equal to I think x square. If I take its derivative first, I will have 2x. Then I will take a derivative again. Then I will get 2. In the second case, let's change its inflection point. Let's say it's equal to minus of x square plus 4. Okay. So it's dy by dx is equal to minus of 2x. Secondary derivative will be minus of 2x. So by this derivative, we know its maxima is going to be at 2x. But from this, we are going to know that it is actually minima because its sign is positive. If your double derivative comes out to be positive, means it's a minima. If your double derivative comes out to be negative, it means it's a maxima. So we know whether, by taking extra derivative, we know whether it's a maxima or a minima. And from this, we know where it is going to come. And this part, we know where it is going to come.
That was a very good explanation, I think. Right. So you take the first derivative to know that you're at an inflection point, right?
At an inflection point or not, and then you, by taking derivative, you know whether it's a maximum or a minimum.
Right. So that's of course very important for any ascent or descent operation, right? Like you think of any gradient descent, then you need to know where you've reached the optimum, right? So you need to have the derivative equals 0.
Right, Hessian equals 0.
and this is
Right, so Radhika drew the other part where you have something like x cubed, right? And has an inflection point at 0. The derivative is 0.
0 point is also 0.
But 1 point is 2 dimensional. One more 相同一个.
Okay, are we all okay with this? So yeah, when the math gets thrown around fast and furious, it's really hard to keep on following. But if you just remember, Jacobian is like the first derivative, the Hessian is just the second derivative. Jacobian is like velocity, and Hessian is like acceleration. That's it, right? Okay.
So continue.
Because of that.
Just give the parameter. So next he used the like he said the chain rule is actually Preprocessing is just chain rule. So instead of using the approximation, you use the actual derivative of the equation instead of using Yeah, instead of approximating it. This will work, but it's a bit slow. Yeah, he ran a few examples on it. And it was changing, but it was changing like it was tending towards the correct answer, but it was very slow. Like even after like 15 epochs, 15 tries of it, it's still quite far off from the answer. Yeah. So
What does he mean by tries versus epochs? I don't quite get that either. Does he mean he ran the entire cross-validation run, or does he mean in one epoch where they went through all the mini batches? So you mentioned Yong Ler just mentioned that what's his name? Jeremy said that he went through 15 tries or whatever and it didn't converge well. What's a try?
Does he mean epoch?
Does he mean an epoch? I don't know. So that's what I want to know. Whether you had a mini batch.
I think you went through 15 minutes, then complete the full report. Because it has local maxima and minima and stuck over somewhere.
Sorry, can you say again? I can hear.
He has a local maxima and minimas, and he struck over that.
Okay.
To find a global minima in order to do function.
So basically for this part, use the Excel sheet to run it. So if you want to look at it, it's here. Yeah.
So it's on the Slack channel
Yeah.
under W6 prep. So pull those out.
Macros.
Yeah, I think you have to. And you can take it out of presentation mode first.
Yeah. So basically, this is his Excel sheet that runs this gradient descent. It's quite. This is the finite approximation thing. If you can see the formula, and this is the actual derivative. So he just runs it, and you automatically slowly tend towards the actual answer. But I'm not sure why it's not working now. But that's how it works. So that's about it. Anybody have any questions?
In the video, so he was reaching a sort of plane. Is
A
that
plateau.
that point? Sorry?
A plateau.
Yeah, plateau.
Uh-huh.
So he was doing it, but it says the graph says error by epoch.
Okay, hold on now. Just run. Yeah. Oh yeah, errors by epoch.
Why you want to use sometimes you know.
Sorry, can you speak up?
Oh no, his question was why you need to approximate? Why you need to approximate? And then, instead of differentiating. But I think sometimes you are not able to differentiate the function because the function is not differentiable.
For example, if it's sine, equivalence one is there is discrete. So close forms equation for the.
Oh, but this one he did both.
I did both. Just to check.
Oh.
Then yeah, that's basically. I think this for he ran. It was going. The error was going down, but it didn't reach. I don't think it reached plateau. It was going down at a very slow pace.
Very slow. Okay.
Yeah, but I'm not sure why this is working here. So that's anything more. Then we'll go to the next one, which is like since it's very slow, you add a momentum to it, so that it will be faster. So momentum is basically you use the previous change. You use the previous change and you add it to your change. So if you are going on the right direction, you keep getting faster and faster. Yeah. You can get it. Just I think this is correct. This should be I-1. Sorry. Yeah.
Okay, so that has nothing to do with the momentum method of
Momentum theory.
It is not a moment. I don't want a moment.
Yeah, it's moment. Oh, never mind. I
Okay.
got very confused.
No, it's okay. It's a translation error, right?
Yeah.
So it's a momentum term is exactly the same thing as in normal mechanical physics, right? So it's just that the object has been moving in that direction because the velocity and the acceleration has lined up, right? So you can keep that term. So you don't have a point-wise change in direction as soon as the gradient changes. It's basically that every time the parameters move, you consider a point estimate, right? So you're considering the previous points estimate, right? So that's a momentum term that just considers the velocity from the last update. But you can also do second order effects, right? So you've heard about that as well, right? Second order just means that just like we just right now are taking in the Jacobian into account, right? The velocity of the ball, if you will, the parameters, set of parameters from the last update. You also want to take into account the acceleration, right? Because that's a second order derivative, right? The Hessian. So if you want to do that, of course, that means you have to differentiate your Jacobian, right? So it's more intensive, right? So a lot of these, you'll find that quick and dirty solutions work probably better, right? Because they say you can get more computations in, and that helps you treat more data rather than get a more exact approximation of something that you don't need exact values for. Right?
So it's just the same as previous, except you add this term in. Yeah. So I'll just continue. So after that, he talked about Adam. For Adam, it's a bit more complicated. So basically, you use the linear interpolation of the previous momentum and the previous momentum and your change. Then after that, you also do it for the square. Then after that, you minus the over square root of this. You do it like something like this. So it's a bit complicated.
Y squared. Is it the second derivative of square?
No, it's the derivative square.
Huh?
Square of the derivative.
Anyone want to try to look that up while we talk? Why does Adam do that? I'm not familiar with Adam. I just know people use it. That's the extent of my knowledge of that. Manage.
What is P?
P is just the linear interpolation. Yeah, it's just a random term for you to. Yeah.
It's like you can. It's like
can
you're
just
trying to
adjust it.
split a fraction of it.
Yeah.
Yeah, like 0.25 and then 0.75. And if you expand out the atom thing, then you get 0.7. Did I give a wrong explanation?
Yeah. Just like how much percentage you want to give to your differentiation term and how much percentage you want to give to your momentum term for them, for your this momentum.
That was the previous terms of.
Yeah. This is previous term. This is the current term. This is the previous term. So use your current term and the previous term.
Can't
a
you
A
have
times
different
1 minus
parameters in this two lines?
actually flush.
Yeah, sorry.
Oh yeah.
Don't you? Like the last
The
one
one
is
is the momentum, the other one is atom.
Yeah.
You could have different parameters.
Yeah, it could have different. I just wanted to make it like easier to understand because there's A and there's B. Okay, I mean this will make it. Yeah, you can have different. Yeah.
So I think now the square is really just for the scaling on the square basis. So like if
Negative.
the gradient is too high, then you slow down the amount of momentum you keep. Something like that. That's like
I think the effect of the square is mainly to
to
deal with the
dampen the
negative and
momentum.
positive is different. So maybe we can think from this point of view.
Oh yeah, because you square root it.
Now it's a
Yeah,
square
square
also.
root. But it's adding and square rooting, right? It's not the same. It's not the
Yeah,
same.
it's not the same.
Yeah, it's not the same. It's,
Yeah, it
you
works
square
out.
then you plus.
It's an imperative.
Empirical analysis.
Right, and checking. Why in square? Why and square?
Go hit Stack Overflow.
This
That is.
Last semester when we did the vision course, I think the Stanford lecturers did tell us a little bit about momentum, Nesterov momentum, and atom. They had at least one lecture on that. So if you do have time, you might want to look at that lecture. I've already forgotten what it means.
So actually,
the what you check? The squaring. Yeah. Would expand on it. Oh, so you expand got the
No, this will
Is that
get
the
this
square?
will get more and more. You expand it.
yeah, correct. You declare. Quite used quite often on the P1 minus P.
Okay. So you guys may want to try to connect this with a little bit of your own experience, right? Like which optimizers work well in a bumpy landscape, which ones work well in a smooth landscape. And then when you generalize from that to your data sets, what does it mean, right? Like there might be some data sets that you have where the optimization looks more bumpy than others. Okay. You have a few more slides,
Yeah.
right? 15.
What? One.
What's that?
You've got another
Okay.
5 or 10 minutes.
Next, he talked about weight decay, which is using the square of all the sum multiplied by a weight decay coefficient. So I think this is more of machine learning than, yeah, he didn't really go into in depth of what weight decay is. Just briefly mentioned that it is also a called L2 regularization. Yeah, so you put that into your loss function, this equation. Initially, it's just the error square. Then you put this, you sum the squares of order. So it in a sense, I think I'm not wrong.
So we went over a little bit of regularization, I think 2 weeks ago or something like that. Why do we need it, right? We are trying to keep our coefficients W to a reasonable amount, right? And the error term, the weight decay term, pretty much forces or penalizes cases where you're setting particular W's, components of W high, right? As you're squaring their value, right? If you have a W term be a large term, when you square it, it's going to blow up, and that makes the loss really bad. So we want to keep the terms in W fairly small because, again, it's like we saw earlier, we don't want very jagged polynomial functions in our values because they're going to be able to fit noise and not a general trend that we expect to see from data, right? So there are several different forms of regularization. They're all based on metric norms. So the second metric norm is the L2 norm, right? Which is basically, Euclidean distance, right? So you square things. L1 norm is another one. That means you just take the Manhattan distance, distance component-wise individually and penalize those. And there are good reasons to do both of them. Again, maybe it's a little bit too much to say right now, but basically, when you believe that all of the different parameters are consistent with each other, like they're all representing pixels or they're all representing dimensions of random word embeddings or embeddings in general, then using something like L2 is good. Okay. I think Jeremy also mentioned that when you're doing structured data, let's say you have one dimension representing some categorical variable and another one representing some other categorical variable, and those two categories don't have anything to do with each other, then treating the two in the same way would be not a good idea, right? So for example, if one is salary data and another one is zip code, you don't think these two things have anything to do with each other. So it's probably better to set the regularization separately from each component, rather than to take their squared value across all the variables and then constrain it to an amount. Okay, so this is why L2 makes sense for data that's consistent from one source. Maybe like an embedding, right? An embedding could be a categorical variable like a word, but just spread out over many dimensions, right? So in that sense, you would use L2 normalization for all of the things in that represent the embedding for the word, right? Earlier, we had this part where we were concatenating two vectors together, right? So if those two vectors mean two separate things, like one is a user, one is a movie, I don't think you should be applying L2 normalization to the whole thing. It might make sense to make L2 normalization for each of the component vectors, and then enforce that the weights for each of those separate components should be within some value. Because otherwise, you're basically saying everything in the vector is of the same thing, right? And I'm constraining them all. So it could be that you inadvertently dampen out the user information too much or something like that. Okay. Yeah.
Yeah, I just checked shortly the Adam paper, and they actually, so this time it might be the other typical argument, the squared makes the math work. So they actually show a theoretical bound on the loss in the convergence, and I assume if you put the squared there, then the math goes there.
Okay.
So of course that's not a satisfying answer, but at least it's some.
Okay, so
you can show some bounds if you use it like this.
Aha. Okay, so it's mathematically important.
Yeah.
To maybe make it converge or something of that sort. Okay. That's an answer of sorts. Thanks for that.
Not 50 pages.
Yeah, that's okay. We are not trying to pin you down on the math here, but we do want to go a little deeper than what Jeremy has time for. That's why we have this recap class. Right?
Yeah, so Jeremy mentioned that weight decay doesn't work well with Adam because I think it will cause a problem with like this parameter being that he said that it's very bad. It's not good to penalize parameters with high weights unless this will be somehow you'll make it so that Adam wouldn't work. So his solution to it was basically to shift the this is the paper for it. It's some paper. It's called Fixing Wake Decay Regularization in Adam. Yeah, he didn't really go through in depth on how you actually do it. He just mentioned that you just shift it, and I think it should be like that. Yeah, I'm not too sure.
Okay.
Yeah. So yeah, with that, then that's the end. That's the end of the.
Okay, great. So I want to go over things in the Slack channel for a minute. Let's thank our presenters first. So we have some projects that are already incorporated. So I think Joe and Eugene both left already, right? But they're going to look at a memory-based relay chat reply system. This is a hot topic, right? There are lots of people asking for chatbots. I put down one that I wanted to do, but I don't have time. Then Jeffro, Animesh, and Yu Chen are going to do something on character identification. You mean like speaker or speaker identification?
So if you click the link, you see like the task. It's about identifying what pronouns, which pronouns.
Okay, that looks fun. Especially if any friends characters are involved, it's always a good
The data set is
competition.
4 seasons.
Oh, okay. Well, that's a good reason to do it. Yeah.
There's a related humor, I think task 12 or something. Why not pick that up? I don't know.
Friends shows up in a lot of places where you might not think it does. Yeah. Then Jiang Kan is going to do with Herty. Who's Herty? Is
Yeah, she's my classmate in the other module,
Okay.
6208.
I see.
So that module requires a project.
Uh-huh.
Yeah.
Good. Kill two birds with one stone. Why not?
Yeah.
Okay. So we'll look forward to you guys getting more specific later on. You already have quite a detailed write-up, which is good. I guess it's required for that class. Okay. Sylvain is said he's looking for a partner. So yeah, it's perfectly fine not to know much about this part yet. So any of you who don't have a project, Sylvain is right there. So go hit him up for use, right? Make a map of knowledge by parsing Wikipedia, make smartphones able to identify their owner by their walking pattern. Mm-hmm.
So that just an idea, but I don't know if it fits into that and if it's too long. But my idea is that now we can recognize the object.
Mm-hmm.
Quite good at that now. But we can see, so that the computer can see and cannot understand. I take the bottle because it's simple, so we can see it's a bottle, it's a green. We don't know what to do with that yet. So what I want is to link all the concepts. So if there's a bottle, you can know that inside there's something. We can grab it, we can throw it, we can give it to someone. So I want to link a bottle to liquid, water, take it, and so we can know what to do. So we have if you have an impulse with a robot, someone is thirsty, then if he sees the bottle, he knows, okay, I can need for that to do some action.
Okay.
So that's just an idea, so I don't know if it fits or I can implement. I don't know if it's for, because so maybe a bit of background, so I come from France, and so I'm I was in electrical engineering, and I was much more application oriented, so not so much in research. So maybe so that's why like I don't know if this idea is suitable, how long it will take.
So that
So
sounds
you-
like a PhD project rather than a course project. I would say, why don't you try to come up with an embedded small idea within this? So
So that's
it
what
looks
I
a little bit like an embedding project where you're trying to take an item and then find other items that might have the same use or same purpose or things like that. So you could try to do it in some type of two-dimensional thing where you have sets of objects and sets of actions, okay, and then put them in the same semantic space and then see whether you can do something with that. So yeah, I think this is, it's a big idea, but you should probably take one small component, reduce it to something that you can manageably do in 1 week of concerted work, right? Because really that's all the time you have to do a course project is 1 week. And then find an ally in the class, to learn with. I highly encourage you to work together on projects because it's much more fun. And you will learn a lot more with someone else involved.
Just ask just one question. Who already has a project?
Can we have a show of hands who's had a project already? Who's come up with their own projects? Yes? Okay. Who's looking for a project or hasn't decided? Okay. So we've got 1, 2, 3, 4. So the 4 of you may want to talk to each other later. Okay. DF is who?
DF.
DF. Okay. And you guys are going to do manga coloring. No, sorry, processing manga to extract dialogues and translate them. You mean from the image of the manga? Okay.
We might change it around.
Okay.
See how yeah, but like, what is difficult? There's nothing difficult about this, right? So it's just
it doesn't have to be difficult, right? It just has to be you trying to do something with deep learning. That's it.
Oh, okay.
Yeah, it's not meant to be like break ground and then you have to write an archive report and post it on the web. You can if you want, that's fine. But yeah, just apply. And all I want out of this course is that you have some exposure to the technology. And from an academic side, I would like you to think about what that actually means, right? Because Jeremy doesn't actually ask you to think too much about it, right? He says like, just go out and do it. I support that part 100%, but I would like you to just go back a little bit to academics and say, why does it work, right? Okay, good. So that's all from the project channel. Okay, so we'll see you guys all next week on Friday. Thanks for coming.
Yeah, guys, maybe you want to grab some snacks from China.
Okay,
Thank you.
more food. So if you didn't take any of the New Year stuff earlier, please do. Yeah.
Excellent.